Hi, my name is Annette, and I'm going to talk about different numerical systems. The first one is the binary system. Well, digital electronic circuits rely on this system, so we can understand it if we don't understand this binary system deeply. Okay, this is one of the simplest systems. This is because it has a base 2, that means that it only uses two numbers, that is the 0 and the 1. This system is a positionary system. That means that dependent of the position is the real value of the number. In this case, instead of called digits, the number of position in that number, it's called bits. This is a chart where we can find the basic numbers, like translated in binary. Okay, this is an example of how this system works. For example, if we want to write a number, tell me a number, like a basic number.
57.
7. Okay, so 1, 1, 1, 0. And how we know that it's a 7? Because we're gonna multiply the number for the position. This number we're gonna multiply by 1, this by 2, this by 4. So it will be 4, 2, and 1, sorry. And this will be 7. Also, if we have more like position like this, like if we have a 1 here, or maybe 1 here, we have to multiply by the number. And that number will give us the real value of the number. So in this case, if we have these two numbers and maybe this, that is 2, and we're going to use the blank spaces with 0, 0, 0 here, here, and this will be 64, 16, will be, ¿cuánto? 82. Yeah? And this is decimal system, and this will be the binary system. Yeah. Well, decimal system. This is the system that we use daily. It has a base 10. Yeah? And also it's a positionary system. We have an example here. This 10 means the base of the number, of the system. And this, the power that we have in each position, it will be raised depending the position. Here will be the 0, 1, 2, 3, so on, so on, so on, so on. And now hexadecimal system. This system, it has, well, it's also known as hex. It has a base 60, and it uses the first 10 numbers of the decimal system, and then it uses 6 letters. It's used for programmers and also for numbers that describe color and web pages, and the most popular use is the hypertext markup language.
Yeah, an example for programming of that code is the assembler language.
Oh, didn't know. And, okay, here we have an example, and this is also positional system. So it will be the same. This is the base that we have, and then it depends on the position, will be the power. This will be multiplied by 16 to the 0, then this is 16 to the 1, 16 to the second, and then so on and so on. And those are the 3 first numerical systems.
Okay. Hi, my name is Jose Manuel, and I'm going to talk about the gray code. Well, first, the gray code is a similar code that works a similar way to the binary, but the only difference is between each number, the count changed just a bit. This advantage of the gray code allows to encoders to be more easy to detect the changes between misalignments between the shafts or any rotatory device. As you can see here, this is a picture where actual map of bits made by the gray code. Depending of the shaft is reading in its axis, depending of the location of the sensors, they are located in opposite sides of this shaft. This map of bits, you can see the value of the sensors, and then are located and processed to another stage of the encoder. But it's basically to see how it's changed between a certain bit and the binary code. This means that a gray code has a correlation between the binary code and the gray code. Means that there's a different number between a particular binary for the gray code, but it's almost is the same. And this is how a binary map of bits, as we see before, but this is the binary count. The only disadvantage of this part is we have several bits that are changed at the same time. That allows the sensors get an error between the process and read and make another mistake in the process. And here this is the gray code made by map of bits, and this is the representative of the colors between the rows. And this is how the encoder looks like inside. Here on the outside of the inner radius of the encoder, we have encrypted or printed inside of this case the same shape, but in a circular presentation. And the reader emits a light, bounces back to the sensor, and is processed by the microprocessors. And we have to understand how the gray code comes from. And this is how. As you can see here, we have a number of 4 digits of binary, and this means the number 6. And we're gonna convert it to a gray code. The first part, you have to take the 0 and check it below, and this is the first digit of our gray code. The next stage is according to this table, that is the XOR table truth. We're gonna check the last 2 digits of their number and compare 2 of the table, and this is our third digit of the gray code. And then we have to take the middle digits of the binary and then go back again and look for the combination that we have in the middle and put it right here. And this is the third digit of our code. Finally, we have to the first 2 digits, and we have to look for in the table and put it right here. As you can see here, this is how to convert binary to the gray code. And basically, this is how the encoders has to do. Meanwhile, they have to work on the errors, meaning their motor is on. Also, there's a parallelism. That means that if you can make a cross right here, and right here, all this on the gray code, this part is similar to this part. As you can see here, the only difference between all this part is just a bit. I mean, if there's no 1 here and there's no 0 right there, it's the same number. But this one allows us to check if there is on the right side or the left side. Finally, in the encoder example. But it's basically the same. Once you reach the number 7 and between the 8, the table is inverted to the same side, but just one difference of the last digit, that is 1.
Well done.
Well, good night. My name is Roberto, and I'm gonna talk about how to convert decimal numbers to binary numbers. Well, as we know, decimal numbers is the quantity of 10 numbers which are 0 to 9, and in binary numbers we have just 2 numbers which are 1 and 0. Well, how to convert a decimal number, for example 45, to a binary number. First, you have to write down the number. After that, divide it by 2, and it will give us 22. We're gonna get a remainder, which will be 1, and then it will be divided by 2 again, and it will give us 11. Now we're not gonna have a remainder, so it will be a 0. Once again, we divide by 2, and this will be, well, the nearest number will be 5, and the remainder will be 1 to reach 11. Again, divided by 2, 5 over 2, and it will be 2, and we're gonna have a remainder of 1. Again, 2 over 2, it will give us 1, and we're not gonna have a remainder, so this will pass through into here. Well, we have not finished, so now we're gonna place the reminders from right to left, and we'll start with 1, 0, 1, 1, 0, 1. Well, we have not finished. To confirm if the number is correct, we're gonna place the powers of 2, which are 1, 2, again, 1, 2, 4, 8, 16, 32.
To make the
Simple
sum,
which will give us 32 because we have a value there. Then we'll have anything there, plus 8 plus 4, again we don't have anything, plus 1. And this will give us 32 plus 8 will be 40, plus 4, 44. And finally, plus 1 will be 45. That means that the problem is correct. Continuing with the conversions. Now it will be backwards, binary numbers to decimal numbers. For example, we're gonna have a binary number. It will be this one. for changing it to a decimal number, we're just gonna place the powers of 2, which are 2. No, sorry. 1, 2, 4, 8, 16, and 32. Then we're just gonna multiply 1, well, the number which is down, that will be here 1 by 1, will be 1, 2 by 0, no, 2, yeah, 2 by 0, 0, 4 by 1, 4, 8 by 1, 8, 16 by 0, 0, 32 by 1, 32. Now we're gonna just make a simple sum. And this will give us as a result 32 plus 8, 40 plus 444 plus 1, 45. And that's it.
Hi, my name is Erika Rosales, and today I'm going to explain to you how to convert a decimal number into the hexadecimal system. Here we have as example the number 1869. In the right side we have the equivalency between the decimal and the decimal numbers. Here we can notice that from 10 to 15 there are some letters of the alphabet that goes from A to F for the numbers 10 to 15. To solve our first example, we need to divide the number between 16. That is going to be our first step. So we're going to divide 1869 divided by 16. In this case, we're going to obtain as a result 116. Here we're going to obtain as a reminder the number 13. Then we're going to divide our quotient between our base, that is 16. So 116 between 16 will give us 7. And as a reminder, we will have the number 4. In this case, our quotient is smaller than 16. So here the process ends. And to form our decimal number into hexadecimal number, first we have to put in our first position the quotient of the last division we resolve, that in this case is going to be the number 7. Then we're going to start to add all our reminders from the last we obtained until the first reminder we got. In this case, after 7 we're going to have 4, and then our last reminder is the number 13. But we have to put the number in the hexadecimal system. In this case, 13 is equal to D. And to end this exercise, just we have to add the base that we're using, that is the base 16, and this will be our result. Now I'm going to explain to you how to convert the binary number into hexadecimal number. Here we have our first example, that is 101110. The first step that we have to do is to divide our binary number into sections of 4 digits. In this case, to obtain our divisions, we have to start from the right to the left. So we'll start with 0, 1, 1, 1, and this is our first section. Then we're going to the second section. We're going to have 0, 1, and as I said, we need 4 digits. So to complete those 4 digits, we're going to add zeros until we get that quantity. In this case, we're going to add 2 zeros. The next step is to convert the binary number into decimal number. And here we're going to use the powers of the number 2, as Roberto explained. In this case, here we're going to have 2 to the 0, 2 to the 1. Here we'll have 1, 2, 4, and 8. These are the ones that we're going to use. So if we make the sum of these 3 numbers, we'll obtain the number 14. Then, now we have our decimal number. Now we have to put that number into the hexadecimal system. In this case, 14 is equal to E. Now let's continue with our other section. In this case, we just care about the 2 last digits. Here we're going to have 1 and 2. Here, the only number that we care about is the number 2. And this is going to be the same in the hexadecimal number. And to obtain our final hexadecimal number, we're going to put in the first place the first number that we obtained from the first section. In this case, we're going to have 2, and then we're going to add the next hexadecimal digits we obtained from the other sections. In this case, we're going to add the letter E, and to finish this problem, we have to add the base that we're using, and this will be the final result.
Hello, my name is Hernan Diaz, and I'm going to talk about logic gates and systematic symbols. Well, a logic gate is an essential elementary building block of a digital circuit. In addition, a logic gate in electronics is a physical device implementing Boolean operations that is applying logical operations. In this case, we can obtain one or more inputs, whereas we only have a single output. Those are applied in, for example, in transistor or diodes. We can find logical gates in MOSFET and in FET, but we can also find logic gates in mechanical items. Let's continue. In this case, we have the schematic symbols, and in this case, I'm just going to talk about the logic gates. The other ones are just about electronic systems and other things. Yeah. Those are the most common logic gates in the world. This is the AND, this is the OR, and this is the EOR. Those function is very simple. In this case, we obtain input, which is a voltage. In this case, we receive an output, which is another voltage or response. It tells us if the voltage is high or is not high. In this case, it tells us that it's treated, tested. In this case, we receive an input that is 1, and it's just an example, and the output is 0. In the NAND will be the opposite, and this will be 0, 1, and it will be 1. In this case, applying the Boolean algebra between A and B, which are the inputs and outputs. As you can see, the AND is a multiplication between A and B, the OR is a sum between A and B, the NOT is twisted, is another, in the NOR is a sum, and is a twisted, the NAND is opposite. As you can see, twisted is symbol of circle, and this in Boolean algebra is this symbol. In XOR, in this case the XOR is a sum, but it's a special one. In this case, we have a couple examples applying the gates, the G gates. In this case, in the NOT, this is tested. In the input, we have 0, whereas the output will become a 1. If the input we obtain 1, the output will be 0. And now, in the AND, we have two inputs, is 0 and 0, it will be equal to 0. And it's the same thing, unless we have 1 and 1. And the NAND is backward to the AND. As we can see, it will be the same thing. We obtain from the inputs 1, 0, 0, and the output will become a 1. And it's the same thing until we get 1 and 1. As you can see, this is very different. It's because it's treated like this symbol. Well, in this case, for example, in the AND or NAND, if we get a 0, if the A will be 0 and B will be 0, then it will be 0, the output. And if the A will be 0 and B will be 1, it will be 0. Whereas in the NAND, it will be A and 0 and B 0 will be then 1. And the second step, the A is equal to 0 and B is equal to 1. Then the output will be equal to 1. In the NOR gate, it's the same thing as the OR gate, it's the same thing. We obtain 0 and 0 from the input that goes to the output, and it will be equal to 1 in the NOR gate. Whereas in the OR gate, the lower one, we obtain 0 and 0 from B and A, and then the output would become 0.
Hello, I'm Gustavo Ortega and I'm going to talk about the logical circuit foundations. The truth tables. Truth tables help us to understand the behavior of logic gates. They show how the inputs of a logic gate relate to its outputs. The gate inputs are shown in the left column here by the letters A, B, C, and D, and the outputs are in blank because it depends on the logic gates that we use in the circuit. Here we have the most common truth tables of the logic gates, and or exclusive and not. The AND gate is for multiplying, so we will have zeros until the two inputs are 1, like we can see in this table. The gate OR is for adding, so while we have 1 in A or B, we will have 1 in the output. And the OR exclusive is a gate for differences, so when we have different numbers in the inputs, we will have a 1 in the output. And the gate NOR is the negation gate, so when you have 1 in the input, you will have 0 in the output, and vice versa. Now we have the NAND, the NOR, and the NOR exclusive gates that are the same than the AND and OR exclusive, but you will have the negative value that those gates give you. The truth tables can also help us to understand the behavior of combination of logic gates linked together. They are grouped in the same way as before, but this time adding more columns in between the input and output columns. When we have a circuit made of many logical gates, we will have more columns in the table, like we can see here. Now the Boolean algebra. Here we have a group of logical gates, and we can replace them with this equation of number of letters and signs. Also, the Boolean algebra has some basic rules, like we can see here. They are 12. Using these 12 rules, we can simplify the equation that we had before, like we can see here. Following the steps, we can get to the result that is A plus B denied, and replacing them for the numbers we have here the truth table of all the circuit. With the Boolean algebra, we can simplify this big circuit with this small circuit, and that is why it helps us.
Hello, my name is Daniel Sanchez, and I will talk about integrated circuit logic families. First, let's define what is a logic family. A logic family of digital integrated circuit devices is a group of electronic logic gates constructs using one of several different designs, usually with a compatible logic level power supply characteristics within all these families. And then the logic used in electronics, with AND gates, OR gates, XOR gates, and all those kinds that my partners already explained. Then we have to continue with the topics. The digital integrated circuits technology has advanced rapidly from the use of a single transistor, such a basic element of all the integrated circuits. And then the technology is more used for the construction of these circuits. We have two kinds of technology. It's TTL and CMOS. TTL means that means transistor logic. So the basic construction of these elements are the transistors and the most common BJTs. So the logic inside is based on transistors, and its characteristics are power dissipation is usually 10 milliwatts per gate, and then the propagation delays are in the range of 10 nanoseconds, and the voltage level range from 0 to VCC, where VCC is typically 4.75 and to 5.25 volts. And the voltage range for 0 goes from 0 to 0.8, and this creates the logic level 0. The voltage level range from 0 to VCC, where VCC is typically 4.75 volts. So we have our graphic, which we have in all this logic, we have the low and the high states. And the low means voltage from 0. For TTLK specifically, the 0 or the low state goes from 0 to 0.8, and then the high voltage or the high goes from 2 to VCC. So we have 2 volts from our max voltage. And the question is, what happens if we apply 1 volt? 1 volt, 1.5, 1.8, 1.90. What happened in that region? That region is called the prohibited band, and we're not talking about dangerous voltages or something like that. It means that the integrated circuit doesn't know exactly what value deliver at the output. So it will be randomized. It can be or high or low. It depends where is more focused the region. But for that reason, we have to be very careful in the voltage applied to the inputs. For CMOS, which means complementary metal oxide semiconductor, it's another family which is more sensible, and the characteristics are it dissipates low power. The power dissipation is dependent on the power supply, and which is affected by voltage, frequency, and the output load and the inputs. Short propagation delays. It depends on the power supply. The propagation delays are usually around 25 nanoseconds to 50 nanoseconds. So it's faster. And the rise and fall times are controlled. The rise and falls are usually ramps instead of step functions, and they are 20 to 40% longer than the propagation delay. And the noise immunity approaches 50 or 45% to the full logic swing. And the levels of the logical signal will be essentially equal to the power supplied, since the input impedance is so high. And the voltage level range from 0, where VDD is the supply voltage. This allowed level, and this means that it's anywhere between 0 and a third of the total voltage. We have VDD, and the 0 is more exactly, which goes from 0 to 1/3 of the total voltage, and the high level is between 2/3 to VDD. Also, we have a more controlled or more specific prohibited band. What are the differences between CMOS and TTL? Well, CMOS components are typically more expensive than TTL, their equivalents. However, CMOS technology is usually less expensive on a system level due to CMOS chips being smaller and requiring less regulation. CMOS circuits do not draw as much power as TTL circuits, while at the rest. However, CMOS power consumption increases faster with higher clock speeds than TTL does, and lower current draw requires less power supply distribution, therefore causing a simpler and cheaper design. And due to longer rise and fall times, the transmission of digital signals becomes simpler and less expensive with CMOS chips. And finally, CMOS components are more susceptible to damage from electrostatic discharge than TTL components. Thank you.